Good morning, everyone, and thank you for joining us. We'll be starting in just a minute as folks continue to join the call here.
And is there a hard stop at a certain time? What's the expectation?
John, we have this going until 12:30. Obviously want to save a few minutes for questions.
Indeed.
And I think
Sure.
perfect. Thank you. Alrighty. Well, good morning, everyone, and welcome to NGA's Energy Innovation Webinar Series. I'm thrilled to see that we already have a number of folks joining the call, and hopefully a few more as we get into the lunch hour. For those of you who do not know me, my name is Christian Roderick. I'm NGA's Public Affairs Director. On behalf of all of us at NGA, we are delighted to have you join us for the second webinar in our Energy Innovation Webinar Series of conversations designed to explore the transformative technologies and strategies shaping the future of energy. Northeast LDCs are at the forefront of our energy future. They are committed to supporting and achieving the ambitious climate and environmental goals that have been set across our region. From researching and investing in emerging energy fuels and technologies to adopting new strategies to support efficiency and emissions reductions, NGA and our members are leaders regionally and nationally. At NGA, our commitment is to foster an environment of collaboration and forward-thinking dialogue, and this series reflects our dedication to supporting our members as they embrace innovative solutions that not only address today's energy challenges, but also pave the way for a resilient, sustainable future. I would be remiss if I did not take this opportunity to note that this series is an important prelude to our inaugural Energy Innovation Summit, taking place September 25th and 26th in Springfield, Massachusetts. At that event, we will bring together thought leaders, industry experts, and innovators to delve deeper into the forces, technologies, and opportunities driving change in the energy sector. If you're interested in being involved or want to learn more, check out our website. We have a page on it there, or please feel free to reach out directly to me. I would love to hear from you. And as another reminder, this series will be taking place every other Wednesday at the same time throughout the spring. We're adding a couple more events, I think, through into August. So keep an eye out for those changes, and we'll keep you updated through our newsletter, social media, and other avenues. But you can always check the schedule on that website. Now, as we begin, if you have questions, please, we welcome them. Please use the Q&A function, and I will be monitoring that to make sure we address as many of those as we can. And with that, I am pleased to introduce John Ciovacco, President of Aztech Geothermal, who will be providing an introduction to geothermal. John, thank you, and the floor is yours.
All right, I'll grab the screen from you, Chris, and we will get going. So I'm going to go to slideshow on this. So glad to be here, and I'll go through an introduction of myself as a part of the slides. So we'll talk a little bit about the basics of geothermal, and then I'll talk a little bit about the utility applications of it that my company is engaged in. I'm also a board member of NIGEO, which is puts on the annual conference each year. So President of Aztech Geothermal, we're upstate New York, but do work all over the country when it comes to utility work. And I have this is the I'm really famous slide. I get up on stage and talk about these things. You'll be provided this later. My company's done a lot of installation, a lot of turnkey work, so we have a lot of good hands-on experience. And then more recently, we're doing a lot of much larger building projects where we design and consult, and then also are working with about 8 utilities right now, which are considering the transition or alternatives to natural gas as a business model. So it's not a new technology. It's been around really since the beginning of refrigeration. This is just a funny Life magazine cover from 1948, and it's the Miracula. And the Miracula was not that miraculous, but it was really cheap. It was only a couple $1,000s and then another $1,000 to install. So the numbers are nothing like that now, but the technology is really basically the same. It's refrigeration technology that leverages the ground instead of the air, which an air source heat pump might do, or a refrigerator in your kitchen might do. Where does the energy come from for most geothermal systems? The shallow ones that we deal with, where we're not going down trying to create steam to make electricity. We're more just trying to leverage the earth as a thermal battery, and that gets recharged in the summer, and then it gets depleted somewhat in the winter, and the balance of that ends up being something that the mean ground temperature, undisturbed ground temperature that we access tends to be in the around 50 degrees, and a lot of the Northeast is kind of a good round number. It's a little bit lower in colder climates, and it's a little bit warmer. Now, it's kind of like what a cave temperature would be. So if you were in a cave in New York, it might be 52 degrees. If you were in a cave in Miami, which I don't know if they have caves, it might be 77 degrees. So it does affect the starting temperature that these systems are leveraging. But essentially, 52 degrees is pretty warm compared to really cold winter temperatures, and it's pretty cool compared to the summer. And so this is a technology that's going to leverage that. Here are some of the ways that we connect to the ground. Horizontal pipes may be buried in the New York upstate area, maybe 6 feet below the surface. We might put a series of pipes, a little like a radiant floor that's buried, and then that carries the energy into the building instead of closed loop pipes. Vertical is very common. It's not really like that. It's more just a 6-inch borehole, and then we put a pipe down it. So it's not quite as cartoony as this, but that's common. And those tend to be in the 200 range in some parts of the country, but more in the Northeast. We're into the 300 to maybe 850 or even 1,000 feet in depth for those boreholes. We can also leverage surface bodies. If you have individual buildings, you certainly want to be in control of that. There's lots of regulation around that, and you get into rivers and things, but it's a possibility. There's also this thing called direct exchange, where instead of a water circulation, which is what these are showing inside of pipes, you would have copper pipes and you would send the refrigerant directly down. That's probably not something the utilities will mess with, but just to let you know that that is a possibility too. One of the interesting things as we look at working with gas companies is that gas pipes, water pipes, geothermal pipes, kind of all the same pipes. SDR11 is a common one that we use for some of you that are into the gas pipe vernacular. The fusion techniques and things are all basically the same. So that's the principal pipe that's used in our industry. And it's not that it is the most thermally conductive or miraculous in that way, but it ends up not being the rate limiting factor. Actually, how fast temperature moves through the ground ends up being the limiting factor once the pipe equilibrates to that temperature, which is a longer story that we don't have time for today. But plastic pipe that you're familiar with, I guess I would say. So why is there interest in this? A lot of it, and this is from New York, and it might be a year or two back, but essentially as there's lots of thoughts in the Northeast about building electrification, we would go from our current summer peak to potentially a winter peak. And a lot of that would be air source heat pumps or electrification of heating from fossil fuels, which then, and plus electric vehicles are a big component of that too. But at some point that'll drive the electric peak and it'll grow. And the more we see forecasts, that crossover point is sooner and sooner, and the delta between these two is greater and greater. So there's a lot of expense related to that. So there's a lot of interest in trying to electrify buildings that use the least electricity. And so a lot of these assumptions are based on air source heat pumps. If you use ground source heat pumps, you mitigate a lot of that. I wouldn't say that we wouldn't get there eventually, or wouldn't go over the summer peak, but it certainly would happen later and it wouldn't be as great. So that's all based on COP. So that's a coefficient of performance. So if we want to electrify buildings with electric resistance, not that we would use a hairdryer or a toaster, but just to show you that this is essentially a COP of 1. That means for every kilowatt hour, I get 3,412 BTUs. And if I leverage with a heat pump, like with an air source heat pump, then I might get twice that. I might get more a COP of 2. So for every kilowatt hour of energy that this consumes, it gets one of its units from the air and it gets one of them from outside. Ground source heat pumps have just more leverage because we have a milder temperature, especially at the peaks, and the peaks are what drive that electric grid. So we're going to have a 3 to 5 times multiplier. So you could say it's 4 times more efficient. And the good thing about that is that that at least approaches in many parts of the Northeast about cost neutral with natural gas heating. Now, you might say that's not that awesome um, because cost neutral also means no savings. But these are negative savings. Certainly if we electrify buildings with electric resistance from natural gas or even propane, much, much worse. And then air source, we still have what are called negative savings. You would have the customer would be paying more to heat, and then ground source at least gets you level and generally has mild savings. The Framingham project that Eversource is engaged in certainly shows some savings for the customers as a result of the conversion. So that's one of the drivers too. So we want to reduce that peak, and then we also want to have the customer's bill not be higher. Now, you still have lots of questions about you have to install the infrastructure, and how do we pay for that? How do we recover those costs? It's beyond the scope of what we'll talk about today, but certainly something you'll need to grapple with. So the basics of the system is that you've got the circulating water. There's not a pump here. There should be a pump here, but it would circulate the water here, and it would then exchange with refrigerant. The refrigerant is then compressed to make it hot, and then that hot refrigerant would then go to this coil up here, and that's how we would heat a building. Then there's a reversing valve, which basically the hot refrigerant goes to this coil in air conditioning mode, and this coil is cold. Again, a little more detail would need to be given to really get that, but I guess we'll put it in the trust me category. It's like a refrigerator that reverses. It uses electricity, but it's most of the thermal energy when we're heating. 75% of the thermal energy we're heating with is from the ground, and 25% of it is from the compressor. So electricity through mechanical energy, in this case, converted to mechanical, ends up being a certain portion of the energy that we use, but it's leveraging a much larger resource here, hence the higher efficiency. So they're reversible. They have the reversing valve. They also can heat hot water. So as you're heating the air, this is called the de-superheater kind of approach. It can heat hot water. Some systems you can actually have them do 100% hot water, where it'll kind of alternate between heating the air and heating water. And then there's some that when they're doing air conditioning, they can heat water directly because it's essentially a byproduct of air conditioning. Is you're rejecting heat to the ground, and we can reject it to a water tank. This is ever changing and different for all of you that are in different areas. And so I just have my assumptions here. You can plug in your own assumptions kind of thing. But basically the electrification options are highlighted here versus some of the combustion fuel options at a given point in time. So if you look at this, you might say, oh, that's not what we have. That's okay. Good for you. But just understand that usually geothermal is cost competitive with natural gas, but not necessarily a big savings, and actually could be negative savings. This bar could be out more. Air source heat pumps will almost always be a loser against natural gas in almost all markets. And then oil and propane are competitive with air source. And then electric resistance is probably not the way to go just about anywhere from a cost effectiveness standpoint. Air conditioning, this is heating. It depends a little on your location, but maybe it's 30 or 40% lower cost, but it's lower cost really for folks that have central AC. If they didn't have central AC, which a lot of older buildings don't, and they just use window units, sometimes that larger central system, even at the high efficiency of a geothermal system, they might actually have more cost of the air conditioning because they're air conditioning their whole house instead of a couple of rooms. So there's some nuances that we need to look at when we look at a bill impact analysis in converting customers. Keep this going. This is just what's happening in New York. I know the most about that. We also work in Massachusetts. We work in Colorado and Minnesota. Um, but the Utility Thermal Energy Network and Jobs Act, which some of the folks on the call probably are familiar with, but the 7 largest utilities in New York were looking to do pilot projects as part of a law. Where in Massachusetts, which I don't have slides on, was done more through rate cases, where there was proposals made in rate cases, and then those were approved by the DPU in Massachusetts. So this has been driven a little more by a law. There are a number of states, which I'll talk about later, that have laws that are passing that are requiring gas utilities to look into this as an option, as some of you know well. This isn't the most updated, but it's kind of updated. I would say there are about 12, probably fewer than that right now, advancing in New York. And these are pilot projects that are looking at a group of buildings, generally not campuses, even though there are a couple of campuses in there. But so it would be buildings that are privately owned or separately owned, and the utilities are looking to run a geothermal network rather than a natural gas network as the thermal utility. The way we're doing it in New York, we have a stage gate process. I'm not sure I would recommend it, but that's what we're doing. The good thing about it is it puts some order to it, and it gives the regulators a chance to assess what's going on at each stage and then move on. The bad thing about it, in my working through both this and working a lot in Massachusetts, which is maybe the other alternative, is in Massachusetts, the rate case is basically budgeted the ability to do the project essentially through to completion. There ended up being some changes to that, but essentially you knew you were doing the project. You would go to a customer and you would say, hey, we have funding to do this. Are you in? In New York, not as easy because you basically get approved for funding at each stage. So that also leads to a kind of a hesitancy, I would say, when discussing getting customers to sign up for these programs. So the order of it is nice. The having the regulators learn how to create regulation around that, I think that's well thought through. The stage gates as a gate for funding, I think is a problem, and kind of is difficult to get the customer engagement in the way that we have been able to do in Massachusetts. The BDC, which is the Building Decarbonization Coalition, they probably have the best resources to just get a grip on the terminology, examples, legislation. They've got great stuff. They even have a map. I don't think I have it on here, but they've got a resource map. So they show in North America where all these thermal energy networks are located and has some facts about each of them. So it's mostly the US and Canada, but it's some cool stuff to poke around on if you want more information about what's going on. Some of that information is here. There are 8 states that have thermal energy network legislation, I believe, in place. Some of them might be pending as bills, but I think they're in place. So and some of you are subject to some of these, so you're familiar with the ones that are in your area, certainly. But there's definitely a trend. We look at New England, we're looking at a lot of those states have some level of a color going on there. So let's talk a little bit about where these make sense, where they don't make sense, maybe how to think
Hey,
about
John,
it. Yep.
before we jump into this next question, and maybe you're going to answer this a little later, we got one question. Did you say that air conditioning costs may be higher with geothermal compared to room air conditioning? Could you explain that a little bit more?
Yeah, so I'll give you an example. So in Framingham, Massachusetts, for the Eversource pilot, we looked at 24 homes. I'll show you that were on the lower part of this system. This is not great, but these little guys down here are single family homes. Of these 22 buildings, 3 or 4 of them had central air conditioning. The others did not. They had central heating, like baseboard heating with water or steam radiators, but they had window air conditioners. or some kind of portable air conditioner. So let's just pick one. So this little house here, they would use two window AC units in the two bedrooms upstairs 10 nights a year. And then the rest of the time, they didn't run air conditioning. So the geothermal system is much more efficient than a window air conditioner, but they only used it in two bedrooms 10 nights a year. When you put a central air conditioning system in a house, people use it because it's lovely. It dehumidifies the house, it makes the house pleasant. They have this sense that it's going to be really efficient, so they think it won't cost more, but it can certainly cost more than the addition of the kilowatt hours for 10 nights a year in two bedrooms. So it isn't that the system is less efficient and that leads to higher expenses. It's that they're conditioning more space more often than they were previously. Does that make sense?
Yeah, that's great. Thank you.
It's a nuance. When you do bill impact analysis, you really need to know what that building is doing and how the geothermal system will affect it. So the bill impact analysis is reasonably intimate and sophisticated to try to get to do it accurately for heating and cooling and domestic hot water, which is another set of electrification challenges that you need to look at.
So John, the cost that you're paying when you talk about cost,
Yep.
it's based off of the pump on electric cost because you're getting the transfer from free heat from the ground. So is it just more the pump cost? That's the difference?
Yeah, the majority of the cost comes from the compressor. You need to run a compressor. So how do we get 50 degrees to be 120 to 160 degrees here, right? So I say 3/4 of the energy that we heat the house with comes from 50-degree water, right? How did that happen? The magic of that is that this 50 degrees is enough to evaporate refrigerant, but that refrigerant isn't warm, but the energy is in that vapor. When you compress a vapor, you make it hot. And then that heat is then distributed into the house. But 3/4 of that, again, it's kind of like a thermodynamics course. So it's the compressor largely. There's also a pump here, not shown, but that's a very small contribution to circulate the water. And then the utility will have a pump that will send the water around the network, which also kind of figures into the coefficient of performance or the efficiency. But it's running the compressor to allow a mild temperature heat to become a hot heat or hot enough to make. It's the compressor. Just as we've all probably, if you're older, especially, you've driven in a car where when you turn the air conditioning on, the whole car kind of lurches a little because it's a big load. Compressors eat a lot of electricity. Same with air source heat pumps or any air conditioner. It's basically an air conditioner. It's really identical technology to air conditioning. And that's where the electric consumption comes from. And that's the same in an air source heat pump too. So where does it make sense? So it's kind of just a rule that I have is that if you have commonly owned land and buildings, that's a good start, like a campus. But that's not the reality for most of the folks in the call, probably. You have not commonly owned buildings. You have customers that own their land, and they're not all campuses, of course. The second factor that's nice to have is a diversity of load, meaning that you have buildings doing different things at different times. And so you can kind of balance the thermal load. What is not diverse? A neighborhood where all the homes are exactly the same size. That's not diverse. They're going to basically be heating at the same time, cooling at the same time. So that's something to consider. So we like to have interesting buildings, different ones, and then buildings need to be pretty close to each other. How close? Just recognize that it's a very different way to think. Is that the energy that we need to heat and cool buildings? Most of that energy is resident right next to the building. Could be under the building in certain cases, but generally right on the property. Or in the case of a utility, it might be in the neighborhood, or it might be a nearby parking lot or something that we access it from. But we need to have those buildings pretty close to each other to justify the piping between each building. We don't want to, you would never think to put a pipe a tenth of a mile down a road with no connected load. If there's no customers for a tenth of a mile, you're just going to end that network on one side, and then a tenth of a mile later, you'll start another one. There's no reason to go great distances. The distance depends on many factors, but you get a feel for it pretty quickly that, the energy is where the buildings are. There's no reason to pipe at great distances. So one of the things I talk about is that, it's great if we have two of the conditions, but we often don't, right? Where we often don't. So the commonly owned buildings, that almost always gets knocked out. We have to have buildings that are close to each other. Just got to tell you that. But we don't often have the diversity of load. And so we might end up, based on regulatory conditions, not having any of these conditions, and we might do a network. But I would say we need to question why we're doing that, or we need to really be careful that we're not doing a network for network's sake, that we're doing it because it makes sense to network it versus doing individual buildings. You can do individual building geothermal. In most areas that I'm familiar with, the utilities really haven't been granted, from a regulated standpoint, been granted the ability to do individual building geothermal, that they've really been largely required to only engage in networks. And again, that kind of gets us far afield, but I certainly am in conversations about that regularly. What does diversity of load look like? So this is Skidmore College. This is 4 buildings that are networked together, and this is their annual load profile. So this is December 31st, January 1st, and the heating is the red, the cooling is the blue, and then this is the end of the year. So this is every hour of the year, and you'll see this is air conditioning and that's heating. This one has a really different profile. This one is different than that one. And so this is diversity of load. This is what we're talking about. So what do? We end up combining those buildings with one big ground loop, one big series of boreholes that feed into that. And this is what the aggregated load looks like when you combine those buildings, the quad all added together. And you can reduce your number of boreholes, your source energy that you need to make that investment, by say 25%. You might be able to reduce it more than that, depending on the diversity of load, because the buildings complement each other and basically share energy, rather than new energy needs to be produced each time. So that's what we mean by diversity of load. These networks, there's 3 thermal components to it. We need to convert the buildings. This is often the largest single expense, more expensive than these 2 combined, which we'll talk about. So buildings need to be insulated. They need to be air sealed often. They need electrical upgrades. So there's things that might need to happen here, and that can be a big expense. That would be true if it was an air source system as well. It's not specific to geothermal. So as we electrify buildings, this is expensive. The piping is the blue here. So that's just the piping that connects all the buildings together. So it's mains and service lines, and they can be configured in different ways. And then the sources and sinks. We mostly talk about boreholes, but it could be sewer, waste heat recovery. It could be a body of water. And I put some of those here. So those are the 3 main components of a thermal energy network. The 2 that are really the thermal energy network are the piping between the buildings and the thermal sources and sinks. You also need to consider the upgrades to the local electric system. So depending on how you electrify these buildings, there's a reasonable chance that they might need an electrical upgrade, and that having a bunch of buildings that are now electrified, especially as we electrify everything, we electrify, the stove, we electrify the dryer, we electrify the water heater. we need to do some good analysis of that area to make sure that the area is ready to take it. Plus, we should consider demand reduction measures when we design these buildings, like smart panels that might manage the loads of even small buildings to make sure that we don't overload or have to significantly upgrade the local electric network. Now, you're on the gas side of it. Some of you are also on the electric side of it, but you can't ignore this because you could end up with a big problem, of course. Just some examples. This is a siting study that was done a long time ago that Aztech worked with Labella Associates on for NYSEG RG&E. So these are different sites, and then there's lots. I've seen lots of different ways to do this, participated in lots of different ways to do it, but just trying to figure out based on a group of buildings, which is the best place to do that initial pilot. This is one of the pilots, not the most modern slide of this, but one of the pilots in Ithaca, New York, that we're working again with Labella on. And this is a group of buildings. We're using open source here. It's not a closed loop system. So we're using groundwater because of the nature of this site geology, which is a little rare, more common that we do it a different way. And then we're piping between the buildings. This is a project that I'm not sure will go forward, but interesting in that these are more centralized bore fields. So each of these is listed as 300 feet. I think they're going to be deeper than that, but this is concentrated in a parking lot at a big commercial building, and then another source over here that, you know, in some smaller parking lot areas, and then the network between all of these buildings listed here. So looking for some level of diversity again. So different types of buildings, different size buildings. This is in Poughkeepsie, New York. Got 4 bore fields. We probably will end up with 3 bore fields, would be my guess. The piping goes between all the buildings. And again, you can see there are different types of buildings, which is advantageous. These are the loads of those buildings kind of in a 3-dimensional to show the heating and cooling of those buildings and their relativity. So some of them have quite small loads, some of them have much larger loads, but that's good. We want to have a mix of that kind of thing. This is a project that's actually running, the first really of its modern kind. There was one done on Long Island by National Grid some years ago, which is interesting too. This is the pilot in Framingham. This has 3 bore fields, not a great picture, but this bore field here has angled bores to lower the footprint on the parking lot, but increase the amount of earth that you can get. So this goes into the page down at angles. These are about 700 feet in length. These are 600 feet. There's a group here, and then there's a group here by a fire station. And then there's an 8-inch pipe that goes for about a mile underneath the, and then it's about 5 feet top of pipe, I think, on this one. And I have some pictures of that installation. So this is where the angled bores are in the Framingham project. And then the 8-inch pipe goes out over in these directions here. This is more about the drilling. This shows one of the main pipes being installed. It's that 8-inch SDR11. And so they did it in 40-foot lengths. So they butt fused 2 20-foot sticks together and then dropped them in and electrofused to the connection from yesterday. This was a gas piping contractor that did it and used the same personnel, the same equipment that you would use for gas essentially to do it. So certainly a good demonstration of some of the similarities between these types of utilities. I'm not going to go through this in detail. This is a little more detail about how you design the system. Most of them are that one pipe system where you've got water moving in a certain direction, and then buildings are pulling water off of that with their own little pump. So there's central pumping here that moves water around and pumps down into these bore fields. And then the buildings, as they call for heating or cooling, are pulling off of that. So they make this main a little warmer or a little colder as they go. And we just want to make sure that the experience that this building has and this building has isn't different enough. There are other ways, two-pipe systems, which would have a more fair distribution of energy to all the buildings. But the problem with those is it's difficult to get two pipes in the street, especially in existing areas and into cities. So the single pipe is most of the projects that we're engaged with. And then we keep a very tight temperature between the houses. So it's basically the whole thing is sized based on keeping the delta T low, the change in temperature from one building to the next low, so that everybody gets a shot at about the same amount of energy that comes in. Metering is very difficult in these situations. The change in temperatures are not that great, so it's difficult to get metering equipment that measures very accurately. So it's flow and temperature is what you need to measure, and both of those vary quite a lot when you optimize these systems, and the accuracy of those is tough. The utility can do it. You can do it in the pump station. You've got more large amounts of flow. You can control your change in temperature better. But to meter individual small homes, for instance, is actually pretty tough. And there's no real standard for it yet. This is just another diagram that kind of shows this would be the circulator inside the building, and it would pull the water off the main and then put it back into the main, while the main is pushing water around to each of the buildings.
John, how deep is that main?
This is 5 feet top of pipe. And we did a sensitivity analysis on this. 6 feet's a little better, but then you're into safety stuff more. You could make it shallower, but then you would need to increase the amount of antifreeze that you put in, which then has a negative impact on the system. Longer story, but that's the quick. This is a modeling software so this is the buildings are pulling energy off of here. It's getting lower and lower temperature, and then it goes to a bore field. So it recharges it, and then again, it pulls energy off another bore field. So recharge bore fields. And then these are areas of connected buildings. This is another example of that. In the summer, you'll see that it gets hotter and hotter and hotter, and then a bore field cools it down. It kind of recharges it, pulls energy out, and then again, it gets hotter, and then we pull it down. In the winter, same thing, getting colder, colder, colder. That same bore field pulls it up. So we're basically, again, we're leveraging that constant temperature of the earth to keep the temperature that gets distributed to all the buildings relatively even. I'm just going to mostly show you these so we can leave some time for questions. There are standards that are out there, a new standards coming out soon. There's some co-development that's going on right now for these types of systems. There are software programs that we use commonly to design these types of systems. And again, this is a takeaway for everybody. We do formation thermal conductivity tests, so we can drill a borehole and we can test how the ground will give us energy, how it absorbs energy over a 48-hour period. And then I have just a bunch of resources that I'm just going to show you. We just had a conference in Saratoga, and here are 5 sessions that are related to this that we gave, and that's a link that you'll have. This is from the fall of 24, that same things, thermal energy networks. So I run the NIGEO conference, and so I have had a lot of programs, and those are available for download. And you can go to the NIGEO website, and those links will be live when I give the handout out, so people can go and listen to those sessions and then also download their presentations.
Thanks so much, John. We'll definitely be happy to distribute those. As a reminder, folks, any questions, please use the Q&A function. John, I have a question for you.
Yep.
I think Jose's question sort of prompted my thinking on it. We do a lot of public awareness about, construction and risk of hitting a gas strike. What's the risk of a geothermal of hitting that in construction or otherwise, and what are the consequences of something like that?
Yeah, so there's water. It's water, and in most systems they have antifreeze, but not all. Even if you don't have antifreeze, you do treat the water. It's mechanical water. It goes, through heat exchangers and into heat pumps. And so it wouldn't be just water, but it's not terrible. It's not non-toxic. If even propylene glycol, which sounds toxic, but it isn't. It's in Gatorade and things like that. But anything in great concentrations can have a negative environmental impact, but it's minor. Trying to find a leak can be tough if it's a subtle leak, like if it's a fusion joint that's only leaking a little. But we use the same techniques that you use for finding leaks in water systems, municipal water systems. So you're going to use sound, is one of the big things that you use to try to find those leaks. And also you can isolate certain sections of the main and see if you're losing pressure. But we're right now in New York, the utilities I'm working with are developing action plans for things like somebody whacks it with an excavator. What's the mobilization look like to go out there? It's more similar to the gas system than it is different in that way. You don't have the risks associated in the same way, because if some propylene glycol leaks into the ground, it's a relatively minor event, certainly not anything that's explosive, that's for sure. But there's procedures being developed right now to try to figure out how to do that at scale. But we've got lots of geothermal buildings and large geothermal buildings. So there's lots of experience about how to troubleshoot these things and how to deal with it if it gets whacked. But it'll take some time to get it back together, certainly.
That's great. Another question I was sent on the side. What sort of maintenance is typically required on the residential side for a system like this?
So the residential inside the building, are you saying? The heat pump?
Yes.
Yeah, heat pumps are more similar to furnaces and air conditioners than they are anything else. Once they're up and running, it's just so you need to change a filter just like you would in say a fossil fuel furnace. The maintenance of an air conditioning system is almost identical. It just happens to all be in the building. It's a refrigeration system that's in the building. The refrigerant charges are relatively low, so they're usually under 5 pounds. So for instance, a propane canister that you might commonly get for your grill is 20 pounds. So it's a relatively small charge. If it leaks, it's not a big risk or safety hazard. But they're more kitchen refrigerator technology. It's sealed. Most of them are sealed refrigeration systems, so you don't usually touch it unless there's a problem with it. They typically last in the 25-year kind of range. So it's a relatively robust thing. There's no outside equipment is one of the things that helps with it. It's all protected and inside the building, and it doesn't have big temperature fluctuations that tend to wear out and fatigue metal parts. So it's more similar than different from a maintenance standpoint to conventional systems once it's installed.
John, you mentioned on one of your slides, I think it was the RG&E slide, that you actually had to include a natural gas peak. I don't know if a heating system in there. Was that due because the makeup of that area was all kind of like all heating at the same time with no cooling going in? Why would you use an additional heat source?
Yeah, it's really their design choices to make. You never need to, but at some point, if it's a heating dominant annually, you're going to pull more energy out of the ground than you're going to put back in air conditioning. Again, it's kind of a thermal battery. You can reduce the number of boreholes and the expense of the installation of the system if you use a peak shaving boiler. The same is true for a cooling dominant system. If you use a cooling tower or some way to get rid of the heat, it'll reduce the amount of infrastructure that you need to install because it'll shave that. And it's also we talked to the regulators in New York and we just said, we really should, if we want to reduce the cost of these things, because everyone's concerned about that, we need to be able to shave peaks in these smaller networks. As the network builds out, a lot of times you would not need that boiler. So you might install the boiler on the first pilot, but if you expand in all directions, there's a good chance you'll have enough thermal mass between all the buildings that you wouldn't need to run it, essentially. The Eversource pilot has a big electric boiler, And in their first year of operation, it didn't come close to coming on, and I doubt it ever will. But it's good to have it there if you, especially if you're a utility and you want to keep your 3 Rs going.
John, thank you so much. This has been fascinating. We are at 12:31, so I appreciate you giving us an extra minute of your time today. This was a great conversation. We'll be publishing it on our YouTube and distributing it,
Okay.
and any materials you have to share, we will definitely pass those on. So thank you so much for your time. And to attendees, thank you for joining us today. We
Great.
look forward to our next one of these in 2 weeks. And again, feel free to reach out with questions. And thank you all so very much for your time.
All right. Thanks so much. Have a good day.